Hello, and welcome to experiment number 3, Force and Newton's Laws. Again, I'm Craig Kuzminski. I'm one of the SCS Lab instructors, and I'm here this week to introduce you to our experiment. If you have not yet done so, please pause the video and read through the entirety of experiment number 3, Force and Newton's Laws. You'll see an introduction to the experimental portion of this week's lab, followed by some hints about what you should be looking for in the privileged planet film that we will be watching in this week's lab. As a part of this week's experiment, you will be expected to observe or watch the privileged planet and respond to the questions in the lab report. What I would strongly recommend to you is to read each question before coming to lab and watching the video tomorrow. As you see, I've done this already for some of the questions. It would be a good idea to go through the questions and highlight keywords that you might be listening for during the film in order to answer the questions. And so for question 1, it says, describe the appearance of the Earth viewed from the edge of the solar system as photographed by the Voyager satellite. And so some of these key words like Voyager satellite and Earth are going to prime my brain to be listening for that information during the film. Same for question number 2. Describe the implications that modern thinkers like Carl Sagan draw from this image. And so automatically I'm going to be listening for the name Carl Sagan during the video in an attempt to best answer these questions. While you watch the film, you'll be expected to answer each of these questions. And at the end of the film, we will take a moment to briefly discuss questions 1 through 13. You'll then be uploading these questions as a part of your lab report. After we watch the privileged planet, we will be completing the experimental portion of this week's lab. And again, we will be using the photogate timers in order to measure the velocity of a car as it moves from point A to point B across our track. So what you'll see here is a primitive drawing of our setup. Here, the rectangle is a car. And again, on top of the car, we have our flags. The car is tethered to a weight pan that will be suspended over the edge of the desk. You will let go of the car, and the car will move from left to right across the track. As it enters through the first photo gate, it will start the timer, and as it enters through the second photo gate, it will stop the timer. We will be doing this experiment. We will have 4 trials. The first trial will be a single car pulled by a mass of approximately 20 grams. As you can see here in the procedure, the weight pan has a mass of 5 grams, and we'll be adding 15 grams of additional weight to give an overall mass of 20 grams. We're then going to do the same experiment, but this time using a mass of 40 grams to see if that has an impact on the determined acceleration of the car. So if you look here in trial 1, we will have 1 car and a hanging mass of 20 grams. In trial 2, we will have 1 car and a hanging mass of 40 grams. In trials 3 and 4, we will repeat the experiment, but this time using 2 cars, and again, progress from a mass of 20 grams to 40 grams. In order to be successful in your calculations, I strongly encourage you to read through the calculations portion. This will give you a good idea of what to focus on in your preparation. So we'll take a look at our data tables for this week's experiment. Again, you'll be measuring the distance between the 2 photo gates, and you'll record this distance in units of meters. Okay. Our hanging mass is going to be determined in units of grams, and you will be needing to convert that to kilograms. So in 1 kilogram, there are 1,000 grams. You might want to go ahead and set up your work on this table. How will I go from a mass of grams to a desired mass of kilograms? It's always a good idea to rehearse these calculations before attending lab. Additionally, you'll have to at some point determine the mass of a single car. So for trials 1 and 2, this mass will be the same. And then for trials 3 and 4, this mass will be different because we will have the mass of 2 cars. You will determine the time it takes for the cars to travel from point A to point B, and you will calculate the average time. So you'll take the sum and divide it by 2. And then using this information, we will calculate the acceleration. I may have misspoke earlier when I said we were determining the velocity. That is not true. We will be determining the acceleration. using the following formula: 2 times the distance in units of meters divided by time squared. And that'll give us our desired unit of meters per second squared. After all, the entire purpose of this part of the experiment is to determine the relationship of the force that is exerted on an object and the object's mass. And we'll compare the accelerations between our trials to try to draw some concrete relationships. You will also be answering these 3 lab report questions on Newton's second law. I've gone ahead and highlighted some of the important parts here. In part 2, you're actually just defining the word proportional and giving your own unique example. I would really encourage you to think about this and to think about how you want to answer this. Um, you really have a wonderful opportunity to be creative here in how you use the definition of proportional to come up with an example. Finally, just one note about the lab report. The 10th point is the connection that students are asked to make between something that they have learned in the lecture and something that they have experienced or conducted in the lab. And so a great model of how to answer this question is the following. In lecture, we learned about this particular topic. In lab, I saw this on display when I observed the following. And so, kind of like we had a structure for writing our hypothesis during our first experiment, it's good to have an idea of how you want to answer the 10th point each week. Unfortunately, some students only talk about the lab or only talk about lecture and fail to make the connection between the two. And so, in order to receive full credit, you must think about making the connection between what you did or learned in the lab and how that relates back to the lecture. Now, finally, the force problems will be part of the pieces of information that you turn in tomorrow before you leave lab. In these questions, you'll be asked to conduct a series of calculations. And so for part 1, it says calculate the force of gravity on a person whose mass is 95 kilograms at the Earth's surface using Newton's law of universal gravitation. And you can find this equation, equation 5.6, on page 58 of your lecture manual. Now I'm going to write that over here next to page 58 so that you're not looking in your lab manual. This equation is provided in your lecture manual. So you're going to want to make sure that you pick up the correct book. One important note is that in this equation, you will be using the gravitational constant, capital G. You'll be using the provided mass of both the person and the Earth, given in the correct unit of kilograms, 95 kilograms, and 5.98 times 10 to the 4th kilograms. However, your radius unit is given incorrectly. Not incorrectly, it's given to you in units of kilometers. And so to solve this, you will want to be certain that your radius is converted from kilometers to meters. If you want to go ahead and refer back to the math reference portion in your lab manual before coming to class tomorrow, it would be a good idea to determine what the relationship is between kilometers and meters. In part 2, it says state the expected value of acceleration due to gravity on the Earth. This should be fairly intuitive to you at this point. And then in part 3, it says calculate the acceleration. And so in part 3, you're going to calculate the acceleration of a person with a mass of 95 kilograms in free fall on Earth using the force from part 1 to determine what the actual acceleration acting on this person is. And so in number 2, we're using the theoretical or the known acceleration due to gravity. And in part 3, we're actually calculating it using Newton's second law of motion, which is F equals ma. In part 4, you're actually repeating the same type of calculations that you do in questions 1, 2, and 3. Again, you're calculating the force acting on a 95 kilogram person, this time on the moon. The moon has a different radius and a different mass, so we would expect the force acting upon this person to be different. And then in part 5, you're actually asked to compare what you think the acceleration due to gravity on the moon would be compared to the acceleration due to gravity on Earth. In question 6, again, you're asked to calculate the acceleration acting on the person. And then in question 7, it's asking you to compare your answers to part 3 and 6. Did your answers show what you stated in your answer to number 5? Why or why not? Thank you. I hope this video has been helpful in easing any anxiety you may have about this week's experiment. If you have any questions whatsoever, please do not hesitate to reach out to either myself or Mrs. Cruzan, your lab instructor. Thank you and have a great day, everyone.